Hi guys, we are going to see how to design and develop a mobile manipulator for space applications, and this is Rohan Toma, and I present to you this topic. The space exploration is a discovery of exploration of celestial structures in the outer space by developing and growing space technology. The physical exploration of space is conducted by unmanned robotic space probes and human spaceflight. Sputnik 1 was the first artificial Earth satellite launched into the low Earth orbit of 14th October 1957. Space probe is a robotic spacecraft that doesn't orbit Earth but instead explores further into outer space. Now, going into the types of space probes, we got a first flyby. It is a space probe which flies past celestial objects and tells actually what a body looks like. It takes measurement of temperature, light, gravity, mass, magnetic field, atmosphere, and compositions and more. Orbiter. An orbiter is a probe that is sent to a body and continuously orbits it for a duration of its mission life. And in this picture we can see a Cassini that orbited 12 years around the Saturn. Now we got a special space probe called as impactor. An impactor is set to hit a body, and usually an accompanying probe will analyze the effect of its impact. An impactor will disturb the materials, allowing us to find what is composed of in a way that an orbiter and lander couldn't. And here in the picture we can see an L-Cross Lunar Crater Observator and Sensing Satellite by NASA in April 2006. Lander. A lander is a craft that can land on another celestial object and can study the immediate environment. They can take precise geological and meteorological readings and can conduct basic experiments. And in this picture we can see Vikram lander to explore Moon's South Pole by ISRO in 2019. Now coming off our topic, we got a rover. A rover is a space exploration vehicle designed to move across the surface of a planet or other celestial body. Rovers are created to land on another planet besides Earth to find out the information to take samples. We are going to combine a rover with a manipulator shown in this picture. Mobile manipulators form a combination of a static manipulator arm and a mobile platform, which turns a limited workspace into an infinite workspace. Mobile manipulator system is a combination of mechanisms which offer mobility offered by a mobile platform and flexibility offered by a manipulator. Our objective is to design a mobile manipulator which consists of a mobile platform to move on uneven rough terrain environment and a manipulator arm to assist it collecting various samples for conducting experiments. In this picture, we can see the 3D mobile manipulator. The arm consists of multiple components designed for specific purpose. It consists of a gripper for collecting surface samples, and a digger for collecting subsurface samples, and a temperature measuring probe, and a 4 degree of freedom mobile manipulator arm. And we got a camera module and compartment for collecting soil samples, and a 6-field rocker boggy mechanism. These are the dimensions. It is designed in CATIA, keeping the workspace in mind. The software used here is we are going to use a robot operating system which forms the core of our project, and the robot ROS is a robotics middleware. It's a collection of software framework for robotic software development. It provides flexible framework for writing robot software. It provides services designed for heterogeneous computer clusters such as hardware abstraction, low-level device control, implementation of commonly used functionality, message passing between processes, and package management. Here we have used various tools such as CATIA and SYS. The main highlight here is a virtual here USB control. The main purpose of this software is to transport the USB signals from ports of the one device to other via a wireless network, so that when a particular USB device is connected to device 1, it is detected as being connected to the ports of the device 2. Here device 1 is a Raspberry Pi and device 2 is a personal computer. The hardware used here, as you can see, we got a Raspberry Pi and a Logitech H2C270 HD webcam, L298 motor drivers and 10 RPM DC motors, servo motors for camera control. We got a linear actuator and L293 motor driver for linear actuation and a temperature probe. Main highlights of the robotic arm are kinova motors, and here we are going to use a lower variant of 58 diameter of kinova motor. And here you can see the specifications, and we can see the peak torque it delivers is 6.8 newton meter. We are going to design a robotic arm design to match these specifications. Now specifications of the controller are as follows. Now the motors used to build the robotic arm are as shown in the following figure. Here the actuators along with the controller connected to it. Design and analysis of the robotic manipulator arm. The robotic arm is designed in CATIA, analyzed in ANSYS for torque acting on motors and stresses included while performing certain tasks. Initial design for estimation of torques and stresses. The length links are link 1, link 2, link 3, link 4, link 5 are as shown in the following figure. The model is designed based on the available motors of 58 diameter and other electrical equipment. The material we have used is ABS plastic and stainless steel. Now here we go with the transient structural analysis of robotic arm. We can see in this video the robotic arm is analyzed from initial position to the final position over a period of 240 seconds under the influence of gravity. The stress and strain results. The semi-transparent portion shows initial position and the opaque figure shows the final position of the mobile manipulator arm. The variation of the stress and strains over 240 second time period is plotted. The maximum stress is achieved is 6.14 megapascals in the arm, which is far less than the tensile strength of the ABS plastic. Design is proved to be safe. The torque results of all joints are as shown in the following figure. The joints are numbered from 1 to 4. The base towards the end effector and the moments of each joints along X, Y, Z and total moment are colored red, green, blue and purple respectively. There is a noticeable variation of the moment values from 180 second time period because the temperature probe and end effector are set to start moving from 180 second time period. We have concluded that the stock values exceed the maximum value of 6.8 Newton meter, and the maximum value here we have achieved is 20 kilonewton meters, which is far more than the expected value. So we are going to reiterate the design. Now the design is the removal of unnecessary material without change in dimensions. The initial model of the arm is modified taking into consideration dimensions of the motors and flexible flat cable connectors and cutting as much as weight possible to ensure no stress concentration occurs. This is done because the torques obtained in the initial design are way beyond the torque rating of the motors. The torque results of all joints are shown in the following figure, and the same stuff as before. The joints are number 1 to 4 of the base towards the end effector. The moments at the each joints of X, Y, Z and total moment are colored in red, green, blue and purple respectively. And there is a noticeable variation of moment values from 50 second time period because joint 4 temperature measuring probe and effectors start moving from 50 second time. Now the torques exceeded. Still, the final design with the modified dimensions of material is reduced dimensions suitable for a workplace and is moving on motors. The provision for incorporation of the various temperature is also removed for weight optimization of the arm. The material of the motor cylinders was changed to aluminium and made hollow such that the weight matches to that of the actual motors that are being used in the arm. The modified link lengths of the arm are shown in the figure. The robotic arm is designed with the help of ABS plastic, which is used for 3D print, and aluminium. Now the movement of the arm from the default position to the bottom position. The positions are labeled as A for the bottom position and D for the default position and position B for the right compartment side of the arm. The analysis was carried out by using the arm as shown over a period of 20 seconds under influence of the gravity. Here this shows the dynamic analysis of robotic arm in ANSYS while moving to position B. The maximum value of stress reached during the arm motion are 0.73 megapascals and 0.9 megapascals, which are far less than the 40 megapascals, which is the tensile strength of ABS plastic. Torque results on all joints in case 1. The joints are numbered from 1 to 4 for the base, end effector movements along the X, Y, Z. Total movements are colored red, green, blue and purple respectively. There is a noticeable variation in the movement values from 50 seconds in the joint 4 because the temperature measuring probe and the end effector were start moving. Here you can see the values are far less than 6.8 Newton meters, hence we achieved our value by the design. Here you can see the 3D printed design of the arm. As you can see, the motors are embedded in it and every wire is going inside it. Coming to the mechanism to control the robotic arm, the arm is controlled with the help of a robot operating system to communicate between its various components. The master communicates between the components about what to do, when to do, and how to do at the exact precise moment as programmed to our needs. The functions performed by the robotic arm are divided into two parts on the basis of their nature. They are as follows: pick and place operation and digging operation. Now coming to the pick and place operation, the arm is programmed to pick the objects only from a certain location, which is deemed to be optimum by taking into consideration the safety of the arm. Now coming to the algorithm here, we can see that the left and the front piece of the robotic arm in the position A respectively. The position A is configured in such a way that the acute angles between the links are 75 degrees between the link 0 and 1, 280 degrees between link 1 and 2, and 150 degrees between link 2 and 3. Here you can see the algorithm of the robotic arm picking. The start input position and go to the position D. This is a program written for the control of the robotic arm. Pick and place operation is performed by the robotic arm. Now the digging operation, arm is programmed to dig around only from a certain location, which is deemed to be optimum by taking into consideration the safety of the arm. The bottom position is same as the position for pick and place, except where the end effector is switched as shown in the below figure. Video along with the algorithm is shown here. The start input position, go to the position given as the input and send message to Raspberry Pi. Now digging operation is performed by the robotic arm. Now coming to the mobile platform, the rocker boggy mechanism. The term rocker describes the rocking aspect of the larger links present in each suspension system, and the balance the bogey as the rockers are connected to each other and the vehicle chassis through selectively modified differential. The chassis plays a vital role in maintaining the average pitch angle of the both rockers by allowing the rockers to move as per the situation. These are the dimensions of the rocker used. Here we can see the 3D model of the rocker. Now the mobile platform controlled with the help of Raspberry Pi. The rocker bogey mechanism consists of no springs. Stub axles in each wheel allows the chassis to climb over any obstacles such as rocks and ditches and sand. The chassis plays a vital role to maintain an average pitch angle of the both rockers by allowing the both rockers to move as per the situation. Mobile platform with a camera module. Simple universal hook joint representing the camera module in the mechanism as shown in the figure. The platform is fixed with a Raspberry Pi mobile housing platform along with a 12-volt battery and the mobile platform with L298 motor drivers at the back. The final mobile manipulator prototype is designed by combining the robotic arm with the mobile rocker bogey platform. The various components of the compartment for the storage of soil samples, temperature measurement probe, camera module, motor drivers are attached to the platform to form a multi-purpose space explorer. Now the top view of the final prototype is showing all the components. The components, as you can see, are kinova motor controller, a camera module, a Raspberry Pi 4, a power bank and a left compartment. The right compartment, rechargeable battery, robotic arm and temperature measuring probe. Operations dashboard for the manual control of the rover. This shows the complete details of the operation of the manipulator, including the live feed of the camera fixed to the mobile platform. Here, as you can see, the camera live feed and robotic arm operation, the status of the robotic arm and the Raspberry Pi control window. Now the zoom portion of the Raspberry Pi control window is shown here. It consists of a screen shown in the below figure, by means of which we are able to control the Raspberry Pi along with the robotic arm and the different systems present as a camera module, the temperature measurement probe, and also steer the mobile platform according to our needs. The demonstration of the camera module and control the live feed. The camera is controlled through on-screen graphical interface slider controls, and the camera feed is displayed wirelessly on the screen. Mobile manipulator prototype testing for pick and place operation. Here you can see the pick and place demonstration of the complete mobile manipulator. Mobile manipulator prototype testing for digging operation. The mobile manipulator is tested by making it perform digging operation while simultaneously moving the platform. Digging operation demonstrated by the complete mobile manipulator is shown here. Testing of the temperature measurement probe. The temperature measurement probe is tested, which is situated on the right side as shown highlighted in the figure. The current prototype is fully functional and can be wirelessly controlled within the range of a wireless network that is connected to it. The image processing and object tracking programs can be incorporated into the rover for making it more intelligent to travel without any human interface, thus making the rover fully autonomous. These are not incorporated in the current prototype due to hardware limitations and compatibility issues. Now we can see the code that has gone into play for making this rover. This project may seem simple, but the complexity lies in the code. Thank you everyone for watching the video, and this is Rohan Thoma.